far, we have been working on foundations, which is sets, logic, and some counting techniques. But now we're moving into the proof part of the course. And as we do, we need to discuss that what mathematics is. Well, when you communicate in math, and that's what I'm talking about here, communicating in mathematics involves very precise language. And this is part of the reason that we spend time talking about logic, where we have the and, or, not, the implication, biconditional. All of these have a very specific meaning. But as you write throughout this semester, okay, the precise language involves using complete sentences. And sometimes you could use symbols and it's sentences, but it should read as a sentence. It also involves using words correctly, accurately. Now, let me give an example where we can see something failing, I will say. So, what is something that you hear often, or at least I have heard many times, and that is the shortest distance between any 2 points is a straight line. I have heard this before, and it's very likely that you have too. But this is not accurate. This uses words incorrectly. And I like to give this example because we can really realize what's going on if we stop and think. Well, maybe ask yourself, what's wrong with this sentence? This one is a complete sentence, so that is not the issue. The shortest distance between any 2 points is a straight line. Well, there's more than one problem here. You might think, well, you have 2 points, you really mean a line segment. Or you might mean, well, don't you need to specify that the points are distinct? It's not the same point, for instance. And those are issues. But there's fundamentally another one that I want to point out as the main issue that is just wrong. And let's look. The shortest we have distance between any 2 points is. So this reads distance is, and then this. Now, you see how this is not an accurate use of words because distance is distance. This is a non-negative number. And a line is not a number. And so this is the idea is reasonable, but it's not stated accurately. In math, we must state accurately. And if you are submitting something and you lose points because it's not accurate, and after the fact you say, well, you know what I mean. No, 0 points for you know what I mean. Okay, accurate. Use words correctly, write incomplete sentences. This is how we communicate mathematics. Now, if we are going to use words correctly, which is a very important part of this course, we need to begin with some definitions. So let's talk about some definitions now. Let's start with the integers, which we have discussed this notation and the set of the integers. This was the first day of class. Now, some definitions. An integer, let's say y, is even provided there exists an integer k such that y is 2k. This is the definition of even. Now, similarly, let's just immediately move into another definition. An integer y is odd. Well, try and guess this before I write. Is provided there exists an integer k such that y is 2k plus 1. So for example, 50 is even, as 25 is an integer and 50 is 2 times 25. Or another example. -7 is odd as, well, this one I need to think a little bit. I want -7 to be 2 times something plus 1. And so this will be -4. Okay, so as -4 is an integer, and then we have this. -7 is 2 times -4 plus 1. So this is definition of even and odd, and this we will use in our proofs. Before I get into some more definitions involving integers, and there are still a few more I want to discuss, let me just mention something we may use about the integers, and this is quite important. Okay, this is a statement about the integers. If we have two integers, let's suppose x and y are integers. Immediately, I know the following. I can multiply, I can subtract, and I can add. And all of these are integers. We kind of see this here, 2k plus 1. Okay, but take any integers, multiply, subtract, add, and you have an integer. And this is something we can use. For instance, and we will even see in our proofs of even and odd that we use this. But be careful because, and this will lead into our next definition, this is not guaranteed to be in Z. So that's something you cannot use. If you wind up dividing two integers, first of all, y better not be 0. But say even you know that y is non-zero, you still can't conclude it's an integer. Take 1 and 2, 1/2, not an integer. This would be rational number provided y is non-zero, but that is not an operation that will land us back into the integers. We may multiply, we may subtract, we may add. Now, we want to have this idea of divides and speak about integers. And this moves into the next definition. Let a and b be integers. We say a divides b. This is what I am defining, and this is written like this. A divides b, provided there exists an integer with ax equals b. This is what it means to divide. The idea is that b over a is an integer, right? Think about b over a is an integer. We don't actually write that because we cannot divide in the integers. So we say a divides b, and this is written a divides b, provided there is an integer with ax equals b. So for example, 5 divides 10 because 2 is an integer and 5 times 2 is 10. Or -1 divides, well, 8, as -8 is an integer and -1 times -8 is 8. We also have, let's see, 0 divides 0. Now this one is not, you don't want to think 0 over 0 is an integer, right? That wasn't the definition of divides, but this is true. The definition, well, take anything. 1 is in Z, and 0 times 1 is 0. Well, what else can I say? Just as a comment, not every integer divides every other integer. So we also have this. 4 does not divide 7. There is no integer with 4x equals 7. No integer x. Okay, and this symbol does not divide. 0 does not divide 5, as there is no integer with, well, we would need 0x equals 5. This is definitely, we have no integer like this. But it is the case that 5 divides 0, as 0 is an integer and 5 times 0 is 0. So here are just some examples thinking about this A divides B definition. Two more things to point out is when we are in this situation, A divides B, we say A is a divisor, or sometimes you will hear factor of B, and B, this one, is a multiple of A. Now immediately we can move into the definition of a prime number, an integer. Say P bigger than 1 is prime provided the only positive divisors of P are 1 and P. This is the definition of a prime number. Now, what are some examples? Okay, 2 is a prime number. In fact, it's the only even prime number. We can prove that, and we will prove that. 3 is prime, 5 is prime, 7 is prime, not 9. That 3 is a positive divisor of 9. That is not just 1 and 9, right? 11 is prime, 13 is prime, things like this. In fact, there are infinitely many prime numbers. As an interesting fact or interesting piece of information, this is, at least to my knowledge, this is still current, the largest known prime number. This is enormous. It's to raise to this power here, which the power alone has 8 digits, and then minus 1. Yeah, okay, that's pretty fascinating in my opinion. One more thing to mention, this is a final definition regarding integers is, well, let's see, I talked about prime, this definition, and the other one I will mention is composite. So an integer, let's say x bigger than 1 is composite if it is not prime. Now, that is stating a definition in terms of not being something else, but I could restate this part, just this part, another way. So in other words, what does this mean? It means there exists, let's say, n integer with n strictly between 1 and x, and n divides x. This would say x is not prime, and this is the notion of composite. As a quick example, 22 is composite as 2 divides 22. Well, in fact, 2 times 11 is 22, and 11 is an integer. What else? 51 is composite as 3 divides 51. 3 times 17 is 51, and 17 is an integer. 0, 1, these are both neither prime nor composite. Prime and composite are notions for integers bigger than 1. 2 is prime, 3 is prime, 4 is composite because 4 is 2 times 2, like this, okay? We have been talking about definitions, and so my next question is, what is a theorem? Well, a theorem, this is a true statement, and statements, this goes back to our chapter on logic, is a true statement for which there is a proof. Now, let me just maybe mention some theorems that you may have seen in other courses. Let's see, if you've had Calc 1, for instance, if f of x is differentiable at x equals a, then the function is continuous at x equals a. This is a theorem, and you could prove it using, say, the limit definition of the derivative. You can use that and then show the function is continuous. For instance, what's another example? Well, from Calc 2, which is my personal favorite of the three calculuses, there's one that says if, let's say, the limit as n goes to infinity of an is not equal to 0, then if you look at the sum of ak, this diverges. And this, similarly, you could prove. We use this in Calc 2. This statement is something called the term test. But even if you've never had Calc 1 or Calc 2, you can still appreciate these as statements, because let's look at these. Both of these theorems are of the same form, really. Okay, here we go. And here we go. And we see a if then. We also look here. Both of these, and of course there are many more theorems in math, but these are two examples that are implications. These are both theorems of the form P implies Q. And our first types of theorems we will prove will be P implies Q. Not these two theorems, but this general form. Okay, so how are we going to prove a P implies Q? Well, we will have a number of techniques. The first is called a direct proof. In a direct proof of an implication, P implies Q, we want to assume P is true. And then we show, using definitions, using arguments, whatever we need to do, but we show Q is true. And this is the strategy. If we assume P is true and show Q is true, we have proved the implication is true. Now you might think, wait, there are other possibilities. Maybe P is not true. And how are we going to prove the implication is true in that case? Well, let's recall what the truth table looks like here. And we will look at the possibilities. We have 4 possibilities, 4 inputs. P can be true or false, and Q can also be true or false. And the implication is false only one time. It's right here where P is true and Q is false, and every other time the implication is true. So the strategy in a direct proof is you just have to make sure that this is not happening here, right? This one. So we assume here, we assume we are in one of these two. And then through our logical argument that's complete sentences and uses definitions, we conclude that this cannot happen and we are only in this situation. And then we would have proved, because this can't happen, so we only have these T possibilities. The implication is true. This is the strategy. Let's do some examples. Here's our first proof of an implication. If n is odd, so for integers n, if n is odd, then n squared is odd. Well, this is definitely an implication. Here's P, here's Q. We will prove this directly. Assume P is true, and then show Q is true. Proof. Well, let's let n and z be odd. Now, I work with just one but it is arbitrary. You don't want to work with 3 and then say 3 is odd, 3 squared is odd. That's not a proof. That's an example. You need to work with an arbitrary odd integer. And so this would be using the definition of odd. Then there exists an x in Z with n is 2x plus 1. Definition. Then, well, we want something about n squared. So n squared is 2x plus 1 squared. If I multiply this out, I see 4x squared plus, there's a 4x plus 1. Now, I want to prove n squared is odd. To do this, it's definition. I want n squared as 2 times an integer plus 1. Right now, I have it as this. So all I need to do is make sure I write it as 2 times an integer plus 1, right? I have it as 2 times something plus 1, and then I need to make a statement as to why this is an integer. This is part of the definition. So maybe comma, which is odd, as 2x squared plus 2x is an integer. This is an integer. Well, we stated x was, and this is one of the things that we mentioned. If you add, multiply, or subtract integers, you land yourself back in the integers. So thus, n squared is odd. And this completes our proof. Here's another. We want to prove if n is an integer, or 4 integers n, if n is even, then 3n plus 8 is even. And again, use definitions in this. Here we go. Proof. Let n and z be even. I'm working with just 1, but it's arbitrary. There exists an x in Z with n equals 2x. This is the definition of even. I'm trying to show this is even, so I want 3n plus 8 as 2 times an integer. This is 6x plus 8, which is 2 times 3x plus 4, which is even as 3x plus 4 is an integer. Okay? Definition. 2 times an integer gives me an even integer. So thus we can conclude 3n plus 8 is even. And we have proved this theorem using a direct proof. Here's my next example. For integers a and b, if a and b are even, this means they're both even, then 4 divides the product, a times b. So we have not only even in this, we get to remember the divides definition. Proof. Well, again, direct proof. We assume a and b are both even. So let a be in integers with a and b even. Then, well, we have 2 integers. So there exists x, y, and z with a is 2x and b is 2y. This was using the definition of even really for both a and for b. Okay, now I want to say that 4 divides the product. If I multiply a times b, this is 2x times 2y, which is 4 times I'll write it this way, xy, as x times y is an integer. I take two integers, I multiply them, I get another integer. So as this is an integer, we see that 4 divides this product. This was the definition of, let's see, the definition of 4 divides AB would be there is some integer such that 4 times that integer is A times B. And this is what we have shown in this proof. So this is the end of this proof. Now, before I do another one, and I think I'll do another one with divides, notice in these 3 examples that we have seen, everything is sentences. Sometimes I use symbols, and this is perfectly fine, but everything reads as a sentence. Even this, we see 4 divides A times B. Then there exists X, Y, and Z with, okay? It all reads like sentences, and this is important that your work reads like sentences when you write and submit a proof. Here we have 3 integers, A, B, and C. And we want to prove if A divides B and A divides C, then A divides B plus C. Well, in this example, my P is an and. We have an and here, and then here is the Q. So my assumption, assuming P is true, we know the and is true provided both are true. So I will assume A divides B, and I will also assume A divides C, and then argue until I get that A divides B plus C. Let A, B, C be integers with A divides B and A divides C. There exists X, Y, and Z such that, well, A divides B and then A divides C. Okay? Well, I want to say something about B plus C. B plus C is AX plus AY, which is X plus Y. Now you see X plus Y is an integer, and I have A times an integer equals B plus C, which is exactly the definition of A divides B plus C. As X plus Y is an integer, we have A divides B plus C. And this is the end of our proof.